Awesome, thanks. Thank you, everybody. And thanks, Hackaday, for having me out. Cannot believe this is my first SuperCon. I've never, actually made it out here. Everyone's like, you gotta go to SuperCon. So I'm finally here. I'm very excited to see what everybody else is working on. But before I can do that, I have to give my talk. So without any further ado, let's talk about my stuff. Boggling the Boardhouse. Let's make weird stuff out of PCBs. A quick aside, a little introduction. This is my Twitter bio. Why write a bio slide when I worked so hard on Twitter? Three big takeaways from this. One, I'm an electrical engineer for SparkFun. I've been there for 9 years in March. That's crazy. Two, I wear berets unironically. Three, I like to make weird stuff. And so today we're going to talk about making weird stuff pretty much exclusively out of PCBs. And it turns out the cornerstone of this knowledge is actually drawing weird shapes in your EDA. If you're not familiar with the term EDA, electronic design automation, it's your Eagle, your KiCad, Altium if you're nasty, so it's basically whatever you use for your schematic capture and your board layout. We're going to be talking mostly about board layout. I'm going to be referencing Eagle a lot because it's what I use at SparkFun, so it's what I end up using for most of my personal projects. Although a lot of this knowledge is pretty general, you can use it in KiCad or whatever else you're working with. So what do I mean by weird shapes? Well, basically anything other than a rectangle, right? So the drawing tools in your EDA are basically made to draw rectangles. And if you want anything else in there, you pretty much have to use an external tool to pull in some art from somewhere else. And there are three really popular ways you can do that. The first is to use a tool called SVG to Eagle, which is very useful if you happen to have vector graphics. The second is a tool called Buzzard, which is useful if you have bitmap graphics. And then the third way is to just not use either of those and to just draw it, which I don't suggest at all, except for in very few specialized cases. So the first thing, SVG to Eagle, this is a tool written by Gordon Williams. It is a free open source tool. I believe it's under the MIT license. It might be under the GPL. Anyway, free and open source tool. You might know Gordon Williams as the developer behind Espruino. Also, quick shout out, I think he's got a Kickstarter going on right now for an open hackable wearable, a watch, smartwatch. It's called Bangle, so maybe check that out. Anyway, SVG to Eagle does what it says on the box. Takes a vector graphics file and jams it into Eagle. And it brings it in as an actual polygon object. So where do you get it SVG? Well, vector graphics drawing programs are abundant. I'm talking Adobe Illustrator. I'm talking Inkscape, free and open source under the GPL. CorelDRAW, I guess. You can also get vector graphics out of most popular CAD programs. So you can export like a DXF out of your favorite CAD suite and then bring it into something like Inkscape and export it as an SVG and get that onto your board. Basically, you take your thing in the drawing program, you bring it into SVG to Eagle. It's a little web interface. You can run it right on github.io, or you can download it and run it locally if you're into that. And it exports an Eagle script. You run the script in Eagle, and you get your shape on your board, any layer that you want. So if you're going to use this tool, I highly recommend this video. You can find this on YouTube. It's 20 minutes long. It's going to take you end to end through the process of using that tool to get graphics into Eagle. And there are a few gotchas. So best practices all in this video. Big shout out at Tall, Dark, and Weirdo on Twitter. Smash that like button. Subscribe. Advantages and disadvantages, right? So advantages, small file sizes are always good, right? Vector graphics are pretty small compared to something like a bitmap. Accurate dimensions. If you draw something 5 millimeters in an SVG, it's going to be 5 millimeters when you bring it into Eagle. So for mechanical design, this is very important. Also, creating filled polygons and pores. So especially in your copper layer, where Eagle is going to treat any polygon like a pore, like a ground pore, you want Eagle to recognize it as a polygon and not just as like a big bitmap, a bunch of straight lines or something, because then it will respect your design rules with respect to things like thermals and isolations. Disadvantages, it has to be a vector drawing. So if you're just like scanning the internet looking for like some clip art you can steal and put on a board, you're going to be limited to you're going to have to find something that's an SVG. There's a little bit of fiddling that's required to get things to work nicely in SVG to Eagle. And then finally, moving imported items is a little bit of a pain. So because they do come in as actual polygons, if you like drag select them and you don't get all of the points, you end up like stretching your thing and moving it all over the place. And if you've ever tried to select something on a particular layer in Eagle, you know it's a little bit painful sometimes. The one way around this is that you can just run this script and then copy your polygon into the footprint editor, into the library editor, and make a footprint out of it, and then you can just sort of like click and drag it. The second way you might do this is to use something called Buzzard. I wrote Buzzard for SparkFun, and it is open source, MIT license, and it is designed for PCB painting. So it does really well with bitmaps, or basically any image format. And this is kind of what the workflow looks like. So this is my selfie PCB. A selfie in the top corner there. You bring that into, you just open it in the little web interface. Again, it's on github.io, so you can just run in your browser. And then you can select a different black and white threshold for each layer on your PCB. So it lets you preview the copper layer, the solder mask, and the silk screen all together, and then you can export that as an Eagle library file, and that library has a single component in it that's a footprint that combines all those layers together. So it makes it really easy to deal with, because like a lot of the time you add art at the end of a PCB project because it gets in the way of everything else. With this, it's a little bit easier to deal with because you have like one origin on that footprint, right, where you're not going to accidentally select it when you're moving stuff around. Advantages of this, basically any image format. So it's all built on JavaScript, so anything that you can pull into a canvas object in HTML5, so any like web-friendly image format, it'll open and turn into a rasterized image. It lets you preview and generate all three of those layers at the same time, so you can kind of get a feel for what it's going to look like before you pull it into Eagle, and then finally it exports it, like I said, as a library footprint, so it's all like one thing all mashed together. Disadvantages, big file sizes. So like, big file sizes in Eagle, right, is like a few megabytes, so no big deal, except when you go to actually generate your Gerbers. So you're going to need those Gerbers for the fab house to make your boards. And I have found that if you have a bunch of these rasterized images, which are just made up of, I mean, my thing is just exporting like 1,000 horizontal lines is what it's doing. And they're all grouped together, but when the cam processor goes to actually make those into Gerbers, a cam job that might normally take like 30 seconds can take upwards of 5 minutes. But you're doing that once over the life of a board, hopefully. So, you know, it's not the end of the world. Finally, fixed import resolution. So no matter what the size of your source file or your output is, it's going to scan a fixed number of lines out of that file. So if your source is very small or your output's very large, it can get kind of steppy. And I'm working on that right now, kind of smooth that out and do either a dynamic resolution thing or maybe just make a high-res version of Buzzard that people can use. And while we're talking about Buzzard, I just want to plug the label maker. So it also has a label maker that I built that we use for all of our pins on our boards at SparkFun. And you just put in like comma-separated text, and it makes this little like field of bubbles that you can click on and edit independently, and you can change the font and the size and the shape, and then export it as a library that has all of those footprints in it, so you can put them on your board. It's really handy for labeling pin headers and stuff like that, LEDs. And you put Unicode characters in it, so like little like skull and bones, or a little like anything you want, like emojis. Like it's pretty sweet. So. All right, and the third method is not really a method at all. It's not a trick. It's just draw it, draw it. Just draw it. And it turns out like there are some things that are really easy to draw, like Space Invaders. It's all 90-degree angles, and Eagle loves 90-degree angles. On a grid, are you kidding? It can't believe its luck. So that's just that, right? Advantages, disadvantages. It works in any, like if you can make a footprint, you can make a Space Invader. No external tools required. Great for pixel art. Disadvantages. EDA tools are not drawing tools. I think that's probably going to change a little bit in the coming years with badge life being such a big thing. Like, fingers crossed, we might get like Bezier curves in an EDA, which sounds wild, but I think we could do it if we work together. Okay. Also, you have to draw a thing, which isn't my strong suit, so it's not the best method maybe for some people. But anyway, we've got weird shapes. Good. Now what? Well, you put those weird shapes into different layers in your PCB, and now you can kind of stack the PCBs together, fit them together, and make things in 3 dimensions. Now, the easiest way to do this is with sort of like joinery, like if you imagine you're doing like a woodworking project, except you're using fiberglass. And the way that I like to do this a lot is with this sort of like tab and slot construction, right? Like sort of like a cross-lap joint if you're into woodworking. Which looks like this. So this is a little PCB that I made. You snap all these pieces apart, you put them together, throw a couple fillet solders on there, and you've got like a little robot guy. And it's like a fun little kit. It takes like 5 minutes to put together. I sold a handful of these at Maker Faire San Mateo. Like, kids love these things, and I love them too. I keep them on my desk. So in theory, this is like a really simple thing to do, right? You just make a slot that's the same width as the thickness of your PCB, and then sort of like half the depth that you want the 2 parts to join. Mechanical engineers will know this, but electrical engineers often don't know this. It doesn't work that way, because it turns out if you specify those 2 slots to be exactly the size you want, they're just making these things with an end mill, right? Like, an end mill has to go in there and make that cut, and they like exist in the world and have dimensions. So if they're like bringing that round end mill into a corner, it doesn't actually get into the corner, and you end up with something like this, where you like, this is beautiful, this is what I designed, and this is supposed to work, and then, oh, no, you got this round corner, and now this isn't gonna fit all the way in there. So the way you fix that is you put Mickey Mouse ears on it. And this works really well, and you can draw those Mickey Mouse ears in the dimension layer if you feel like it, but I've found actually what works best is just throw some drill hits on there. So make your slots exactly the size you want them to be, and then throw like 20 or 40 mil drill hits on there, and they'll do the drill hits before they do the mill, and you end up with that nice corner relief that lets everything slot together the way that it's supposed to. So once you've got things fitting together, how do you actually fasten them? Well, solder works really well for this. So there's one thing that you're going to run into, though, with soldering, and it's lifting pads. So a fillet soldering is a lot like fillet welding. So what's a fillet? Well, it's not fillet. It looks like fillet. It's not fillet. It's fillet. It just means a rounded corner. And when you fillet solder something together, you're basically taking 2 surfaces at an angle, and you're filling in that corner with solder to connect them. And when you go to design a joint like this, there are a couple ways you can do it. And this on the left is kind of like what your first approach might be. Just a little island of copper on bare PCB. You put them next to each other and you solder them, right? Like, that works great, except 2 things. One, the strength of the solder joint is not your limiting factor here. It's actually the strength of the glue that's holding the copper to the PCB, because you're going to rip that pad up. And second of all, you're going to get it like way wicked hot when you pour all that solder on there to make that joint, and it's going to delaminate from the board. So how might you fix that? Well, you could make the copper layer much larger and then just cover everything that you don't want to solder with solder mask. And that works great, except that now you have this huge heat sink that makes it very hard to solder. And also, maybe I don't want solder mask there. Like, yeah, that's what solder mask is literally made for, but maybe I want to use it to draw like a cool shape on the board, and I don't want to have all this solder mask all over the place. So it turns out what you can do is you can go back to the like simple method, and you can just sort of do this galaxy brain method over here, where you drop a via in the middle of the pad, and then that via basically acts like a rivet that holds, like goes through the board and holds it on the other side. And so now you're not going to lift the pad when you heat it up, and it's actually kind of acting like a mechanical fastener. And it doesn't take very much real estate. All right, so you've got all these little tiny bits and pieces. You know, one project might have like 40 different little shapes that you have to connect together. you can hand somebody a bag of like 40 different little PCBs if you want to. They're not always psyched about it. So what you might do is give them all on a nice little frame, right? Like this, like plastic model making kits, right? So if you do like Gunpla or like any kind of plastic model building, you might be familiar with sprues. Sprues are what happens when you injection mold things. It's all the channels that the plastic had to get through to get to your parts, and then you just take that whole thing and hand it to somebody, and they can snap out the parts on their own and give them a little bit of sand. Good to go. So we're not injection molding anything, but we can pretend, right? So this is what I did with my robot. I just drew a panel with little sprues on there that connect all of the things together, and then when you want to separate them, everywhere that there's a separation, you just put mouse bites. And mouse bites are little tiny holes all drilled right next to each other. These are what I usually use. They're 20 mil diameter holes spaced 40 mils apart. They snap really easily by hand at sort of that half, what we would generally call like a half thickness PCB, 0.8 millimeter. They do snap by hand at 1.6 millimeter as well, but it helps to have pliers if you want a nice clean break. And you can sand down the edges that are left over. And the thing that you might think is like, well, is the Boardhouse going to care that I have like a whole bunch of holes drilled in this thing really close together? And I was like, they might. So I did this. It's not what it looks like. So this whole thing is actually, it was a lot of work for a really dumb pun. It's sheets of not LSD but LEDs. So what I did is each of these little squares has a little 0603 pad on the back for a resistor and an LED. And then on the front, I replicated the infamous orange sunshine artwork and then drilled, I think it's like 1,096 holes in each board. Boardhouse didn't care at all. They didn't bat an eye, right? Like apparently there are tons of designs out there that have just a ton of vias, especially if you use the auto router. And they don't, so they're used to it. They don't care. So this is the mouse bites is a great way to do that. Okay, so we've done weird shapes in let's see. We've done weird shapes in the dimension layer. We've done weird shapes in the copper layer. Let's play with the mask layer. Okay. So PCBs are made out of fiberglass. And most of them, unless you order those really sexy after dark PCBs from Osh Park, is clear fiberglass. And so it works really well as an LED diffuser. And so if you just draw your favorite shapes in the T-stop and B-stop layers, that's the Eagle nomenclature for the mask stop layers, you can shine an LED through it and you get nice segmented displays. You have to make sure there's no copper under there. And then I found that it also helps to have a sandwich in between where you're just literally milling out a little well for the LED to sit in to stop light from leaking between your segments. So that's a 7-segment display that I made out of PCBs. It's just 0603 LEDs on the bottom with some resistors, and then it's the stack of PCBs right on top of each other. And that's cool, but like I can buy a 7-segment display, and it's cheaper than doing this. But you can make anything you want. So this is my Space Invaders badge. This is 3 layers of PCB with Space Invaders and little bullets all on the top layer. And underneath are just addressable LEDs. I'm using the APA 102 2020 little tiny addressable LEDs. And what's running this is just it's just an ATmega 32U4. It doesn't take a lot of processing power if you have the addressables, right? It's because you're not like maintaining a matrix of LEDs and having to keep them on long enough to see them. So this is a cool thing you could do. Turns out, actually, back in the day when Nintendo was prototyping the Game & Watch games, if you guys remember Game & Watch, they were like those little LCD, like fixed segment display games, kind of like the Tiger electronic games. When they were prototyping those, they actually cut all of the segments out of like smoked acrylic and backlit them with like little grain of wheat bulbs, little incandescent bulbs, because it was cheaper to do that than it was to like have a prototype LCD made every time that they wanted to test the gameplay. So there were all these like models, like desktop size models of all the Game & Watch games. And so like if you think about it, you could do any of your favorite Game & Watch games in this style. Another thing that I did on that project was Bendy Tab Buttons. So this is like my new favorite thing. If you cut like a long finger into a piece of fiberglass, it has a little bit of flex to it, especially if you're doing like a half thickness PCB, like 0.8 millimeter. And then you can bend it down into like a button. So this is a little Arduino clone that I made that has the reset button as a little finger in the top sandwich of this PCB, and then underneath that I actually just soldered like an existing push button module. This is nice because you don't need a lot of travel, so you don't need to really push down on that fiberglass too hard and really flex it. You're just pushing down hard enough to hit that button, and you get the nice tactile feedback that's built into that button module. But if you want to be really cheap, you could just do this. This is what I did on the Space Invaders, the Cosmic Aggressors badge. And so what I've done is on that top layer, it's all just a ground plane, and it's connected to the ground on the bottom layer through the headers that I'm using as rivets to hold the whole thing together. And then I just put a little bit of solder blob on the bottom, and when you flex those, they touch. And then I'm just using the internal pull-ups on the processor, and I know when that pin goes low that you've pressed the button. Luckily, in Cosmic Aggressor, you don't actually move that fast, so I'm pulling that button once every, like, I don't know, tens of milliseconds. So I'm not doing any fancy debouncing or anything, right? Like, this is a really noisy switch. Like, if you hook this up to a scope and like pushed it, like you're like grinding solder into itself, so it's like noise. Doesn't matter for this. So, okay, so you can make contacts for switches. Can you make contacts for wipers? Sure, why not? So this is a rotary encoder made out of PCBs. There's 3 layers. The bottom layer has little surface mount pogo pins, and they contact the encoder track on the middle PCB, and then the top one just retains it mechanically through those standoffs. And while I was at it, I threw some addressable LEDs on the underside of it, and then I addressed those through the metal in the standoffs. And yeah, you can hook this up to Arduino, run the encoder library, and works like a charm, actually. It's a little difficult. Like, if you've never designed a rotary encoder, it turns out like drawing segments of circles to be like the right distance apart is kind of a pain in the ass. I think I did like 4 revs of this before I got one that worked. And what you're going to do is you're going to be like, oh, I'm super clever. I figured out how to do this with only like 2 contacts or 3, and you're not. You're going to rediscover why they're built the way they are. So yeah, this is totally a possibility. Is it economical? Not on its own, probably. Like, you're not going to do this instead of go buy a rotary encoder, but you might do this if you want to make a fancy badge, or if you have like a larger like PCB monstrosity that you want to build an encoder into. You'd totally do this. So stacking boards. All of this has to do with stacking boards. So aside from the kits that I talked about at the beginning, where you're kind of putting boards at perpendicular to each other, everything else that I'm doing is just stacking boards directly on top of each other. And not only does this allow you to get like nice topographic curves out of things, kind of the same way you would if you were like stacking laser cut acrylic. If you're thinking kind of in the same way when you're doing that kind of design. But it also allows you to have like cavities and channels in between the boards. So on the Space Invader Cosmic Aggressor board, you have 3 layers, and 3 layers are actually doing 2 different things in different sections of the board. On the top section with the LEDs, this is the stack up, right? So these are the footprints for the APA 102s. These are little drill hits that act as light wells to hold the LEDs and keep them from shining on each other. And then the top layer is just the nice little like mask. And that's cool. And then you can take out that center layer later in the board, right? And it makes this nice like section, this chasm where you have room to bend these 2 sections together, and that's how you make your switches. So if you go through and sort of like lay out where you want these different features to be, you can get a lot of functionality out of just this handful of boards stacked on top of each other. So that's pretty much all I have time to talk about, I think. But I want to like spare a thought for the poor engineer who's on the business end of your Gerbers, because they're going to have to figure out what the hell you were thinking when you decide to put like 1,000 holes in something, or like put a bunch of V-scores on one end of a board, or like whatever it is you're doing. And so these are some lessons I've learned through like really long email exchanges over the time difference between here and the fab house in China. And one thing is like just check up on what they can do before you ask them to do something and just assume they can do it. Look at things like their drill sizes. A lot of the time you can specify any drill size that you want and they'll just pick whatever is closest out of their catalog. So if you need something with a tight mechanical tolerance, check and see what drill sizes they actually have and specify those. Look at things like the minimum spacing, so like the minimum sort of distance that things can be from each other before they start to bleed together. And that's for basically any layer, right? Like the copper layer, the silk screen, the mask, they're all going to have different, they're all put on with different processes, so they're all going to have sort of different tolerances. Minimum slot width, you know, again, the end mill has dimension in 3 dimensions, right? Like it is a size, so you can't make an infinitely thin slot in a PCB. It's going to be a minimum thickness. Label your V-score lines. Oh, yeah, leave notes, and leave them in a layer that the engineer will see, because you can put a ton of notes, like super nice notes, in your, like, some random layer in Eagle, right? And then you export it to Gerbers, and those notes are just whoosh, they're just in Eagle now. And you send the Gerbers to the production engineer, and he doesn't get any clue as to what you're trying to do. So I found that leaving notes in the copper layer works great, like outside the dimension of your badge, obviously, because they'll just throw them in there. Yeah, in the copper layer, I'll put things like, this is a V-score line. I need this routed out, you know, stuff like that. Oh, yeah, and if 2 pores don't connect, so there's a lot of situations where you'll just have a copper, like a ground plane, and then you're going to put mouse bites in there. And what the production engineer will see is these 2 pores that were supposed to be connected and look like they're going to be connected, but they know, because they're a production engineer, that when you drill all those holes, as the drill goes through, it tears the copper layer, and you don't actually get an electrical connection there. And they're going to warn you about that because they don't want you to ask for a refund. So then you have to email and explain to them, it would be cool if it works, but if it doesn't work, it's not a big deal. Like, that's not something they hear very often, is like, I just want to see if it works, and if it doesn't work, I'm not going to return the boards or anything. So you have to like convince them, like, no, fine, do whatever you want. We'll see, it's an experiment. A lot of the time now, I'll just like put a little keep out around things like that so that it's very obvious that I don't intend for those things to connect. Yeah, I think that's everything I've got. Finally, here's a QR code you can take a picture of if you're into that. It points to this URL, I promise. This is the GitHub repository where I've put up all of these slides, and at some point this weekend, I'm also going to add an Eagle library that's full of like little design features that you can add to your boards, and also examples, links to like all the resources I talk about, and examples of all of these things in different projects that I've done. So keep an eye on that repo. It'll get updated over the next few days, hopefully. I'm going to try. So does this help? I'm just going to, yeah, there you go. Yeah, so that's everything I've got. I think like 3 minutes or something, so if anybody has questions, I can probably take like a few questions, 2 or 3 questions. Yes? How do you keep out? Yeah. Yep. Mm-hmm. So if you, a lot of what you're going to be doing, the question was like, how do you handle a keep out for the copper on the edge of the board when you're doing like those Bendy Tab buttons? And like boardhouses generally don't care how close to the edge you get with the copper pour. But so what you're going to end up doing a lot when you're doing this kind of thing is going in and finding a balance between like explicitly telling your design tool that this is a keep out, like using something like the keep out layer in Eagle, and then also adjusting your general design rules to like make your spacings very small. So generally I'll go into my design rules and I'll just turn off like isolate and make it 0 mil so that everything just runs up straight up against each other, and then I'll go in and explicitly like mark where I want keep outs to be. Yes? Your buzzer software sounds really cool. Any limits to making compatible with Yeah, for sure. I definitely want to do that. I dug into the KiCad style, like the library files a while back for a different project, and I was like, oh, this really isn't that different. So compatibility wise, it shouldn't be like a heavy lift, but I just don't have a ton of time. So I'm going to work on it, but if anyone else wants to work on it, you're welcome to, of course, and send me a pull request. But yes, I do plan to eventually have KiCad functionality there, because I do use KiCad on occasion, especially if I want to make a very large PCB. Autodesk in their infinite wisdom has put a size limit on how big of a PCB you can make in Eagle standard. Any other questions? Yes? So there are a couple ways you can go about attaching multiple layers when they're stacked directly against each other. You can either use SMD pads and then castellated connectors. So castellation, if you're not familiar with that, is basically you make a plated through hole and then you mill half of it away, and you end up with like a plated edge. And the cool thing about castellations is they don't cost extra the way that edge plating does. So a lot of board houses will have a thing where it's like, oh, you can get edge plating. And so you just specify like where along the edge of the board you want the copper to go. And it costs a lot more. But if you just put a really big diameter like plated through hole and then tell them to mill most of it away, you end up with like a little concavity that's plated over the edge. So that's one way you can do it. You have that on the top layer, and then on the bottom layer you have a landing pad for it, and you just sort of put solder in there. Another way to do it is to just put drill hits all the way through all of your boards, and this is what I did for the Space Invaders badge, Cosmic Aggressor badge. I'm gonna do it every time. I just have plated through holes on every layer, and then I put I just take a single pin header and I put it through and solder it on one end, and then smush all the boards together and solder it on the other end and clip it off like a little rivet, and it just sandwiches everything together. And the nice thing about that is it's really simple to just take a soldering iron and touch it real quick and peel that top board back off and take everything apart for repair. I think I can take one more question.
So when you're doing that, how do you get, like, does the solder flow nicely down the rivet?
Not super nicely. So ideally, actually, what you want is you don't really want the solder to flow all the way down the rivet, because then, like, what you really want is to tack it on both sides, and then the middle layers are floating, so that when if you need to take it apart, for whatever reason, like you spilled a Diet Coke on it, just hypothetically, then it's easy to just wick away that solder from the top and take all of your layers apart. If you want the solder to wick down in there, like, you can just flux the heck out of it, and that will work. All right, thank you. I think that's all the time I got.
Thank you so much. Thank you so much, Nick. We're going to take a